Testing. So I guess I should start. So what is the goal today? We were likely to finish this topic. So I will release the last assignment, which essentially just asking you to do computation on regression and ANOVA. And if you know Excel, probably you would not take more than 15 minutes to do all the assignment. I mean, at most half an hour, but I will make the deadline like the noon of Thursday, so that I can put the answer there. Okay, to remind you that assignment is I will drop the lowest one. So if you think you do well for the first 5, so you can basically forget about it, because I will drop the lowest score. Anyway, what do we do today is we will just do some analysis based on regression, because last class we already covered it, how to estimate regression, right? And here we talk about some hypothesis testing and estimation, and that will be the goal of today. Okay, and we will learn use some Excel to do the all the calculations. So let us quickly remind ourselves what is regression. Regression is being a tool that try to understand how two numerical variables are related, right? Education and income both are numeric variables. Advertising and sales, drug dose and recovery time are the 3 examples that I said last class. So I hope you can remind yourself how this related to ANOVA, right? I mean, just in case you don't remember, I think it's good to look at this diagram again, since it is pretty useful to distinguish the two, right? So if you have the data of, I say, the following, right? You have people's education levels and their income. Likely you will see maybe group of high school dropout will be here, right? If the education level at high school. And this is their, say, meal of high school, right? And you will have bunch of data that people graduate from university, right? Right, maybe the mean is here, meal of uni. And maybe here's a bunch of people who have a master degree, right? And what ANOVA said is 3 different groups of graduates, they have different mean, and we can use ANOVA to distinguish 3 of them, right? The question is, okay, because the grouping has no meaning, right, in general, so you cannot say much, right? But for education level, it's clearly, at least it's the ordinal data, right? The order actually matters. And actually we can quantify the order and make the education level be the number of years in schools. And in that case, it's good to have a formula how you relate income and education level, right? So basically is what you want is I want to fit a linear line such that income equal to alpha plus beta education edu plus, right? So that is, I want to have a formula like this, right? So that means that I actually, it's the goal of regression, try to find a line, okay? That is the main idea of this, right? Is to find a line that would best fit the scatter plot, right? And how do we define the best fit is by vertical distance, right? And the reason is being that we're trying to explain different levels of income, right? So it's not explain education level, rather we are using educational level to explain income. So the accuracy of your model is the vertical distance rather than horizontal or perpendicular distance, right? So the vertical distance is the reason because we use education to explain income. And we want square distance because we don't want to handle absolute values, and because the math is much easier. And that's why the least square method tells us is to minimize the vertical distance, right? So we define, say, suppose this is D1 and say this is D2, right? Then what you're doing to do is to minimize, right? Choosing alpha and beta, okay? And make it consistent with your notes. I use A and B, okay? A and B here, right? A and B here. I want to find A and B, okay, such that D1 square plus D2 square, so on and so forth, right? All the vertical square distance is being minimized will be the goal of the least square, okay? And here you can see we do not have any probability there, okay? Just basically the best fit line, okay? So that is the least square method. Have no assumption on how the data being generated, okay? There's no bell curve is being assumed anywhere in the model, just to minimize the vertical distance. So it's nothing about probability, just mathematical result, right? And what is A and B? Actually, I think it's going to go to slide to tell you what's A and B here, okay? And the A and B turn out to be something I would say that would be very natural. Is the line actually would pass through the center of data, x bar, y bar, which is given from the first equations. The first equation tells you the line that would best fit in terms of minimizing the vertical distance will be the one passing through the center, x bar, y bar, right? It will passing through x bar, y bar. And what would be the B, okay? And the slope, okay? A is the intercept, B is the slope, right? The slope turned out to be directly proportional to the covariance, right? If you try to write that, this is the formula, right? Covariance. And probably is easy to see because actually pass through the center, right? So basically, if it is above the mean for x and y at the same time, B should be positive, right? If they both are below the mean at the same time, right, and above the same time, it should be a positively sloped line. And if one is above, one is below, right, then it'd be negative slope, right? That's what we learned from covariance idea. And the reason why you divide it by variance, right, is basically the scale. And the reason is being that if you double the variance, right, and the curve will be the slope will be sheaf a little bit rotated, much more flatter. So that would be the main idea. I guess it's good to look at the graph again. Say this, the first one demonstrate the idea that the best fit line will pass through the center of data. Okay. And the second one again demonstrate if this is the case, actually is positive covariance, right? The point actually is more likely to be here, the purple region, and out compared to purple outside the pink region, right? Likely to in the pink region. And pink region actually means they have positive covariance, right? Outside the pink region, then it will be negative covariance, right? So that's why B should be positively related to covariance. And easily you will see if covariance is 0, the line you fit should be 0 because X and Y have no relationship, linear relationship. So that means that your A will be Y bar, right? The reason is being here if covariance 0, B is 0. When B is look at the equation, Y minus A is equal to Y bar minus 0. So for this equation, then actually A will be Y bar. Okay. So yeah, that means that the line, the best fit the model will be just Y bar. That means that your Y is unrelated to X, right? So X telling us nothing, right? Essentially, it's like the ANOVA, being the null is not rejected, right? The grouping by X has whatever meaning doesn't exist. Okay. And this is the covariance negative. I think that is rather clear to us. I don't think we would be too much worried about this part. And this idea of variance, okay? First, do note that your line of regression must pass through the X bar, Y bar, right? Because that's coming from the optimization. And if you keep the X bar the same, Y bar the same, you increase variance X. It means that every observation, okay, relative to X bar, the horizontal distance would move outward, okay? And in that case, for observation, all move away from X bar. And then if you try to draw a line, it must be the case that the line is more flatter, right? So that's why increased variance will make the line very flat. In the very special case where you increase variance so large, right? We're far away, right? Imagine the line actually something like here, right? And compared to here, right? And your line will be even fatter, right? So remember, you have to pass through the mean. So that's why if you keep increasing the variance and keep other things the same, then the line would be more flat. Okay. And here it just some consequence of if you double X. I think it's a little bit difficult if you don't see the math, but if you able to see the math, if you X multiplied by, say, 4 times, say for example, by 4, right? And you can take out 4 in the numerator, you can take out 16 in the denominator, so the whole coefficient is reduced by a quarter. Okay, so just basically as what we have expect here, if you double the data, right? So here, right? Suppose this is X. Now you consider case well, now you have 2X, right? So everything is double, right? And turn out the slope is just half of it should be, right? Because it's rotate a little bit, right? Rotate a flatter one. So that would be the main idea of this graph try to show you, but I guess it's not. If you know the formula, everything is there. Okay, so this is already a formula that shows you everything we want to show you. Okay, so and if you have y every number increased by 1, then a increased by 1. So we just having shift up, then the line will shift up, right? So basically coming from the first equation, right? If you everything y shift up by 1, this expression would not change because y go up by 1 and y bar also go up by 1, right? This b will keep the same, the slope is the same. And the intercept will go up by 1 because this is not changing, this is not changing, this only changed by 1. So a go up by 1, right? So of course, if you if you see the math, that would be very simple. But if you don't see the math, I think it's also very simple because the graph already tells you, right? If you everything shift by 1, the only thing changed is the intercept shift by 1, right? I think shouldn't be a puzzling for you to see these facts, okay? But so I think last time we talked about how to find this slope by using the function slope and intercept, right? And later today we will talk about Excel add-in later, which also give you all the information quickly. Okay, I hope that is done with the least square. So here we have a probability model, okay, trying to tell you what it is. I guess it would be good to look at the model compared to ANOVA, okay, just to. So ANOVA, what we learned, the model is like the following, right? Each observation from group I, okay, is coming from mean of group I, right, plus some error term there, right? And usually we assume, as for inference, we assume this is a normal sigma, a bell curve, right? And the extra assumption we have to make, right, is that actually means this is 0, right? And variance is the same for the different group. They share the same variance. And the next one is each group is independent, so different group would not be 0, right? So this is the ANOVA model, right? So every observation you see from group I will be basically coming from some mu I group mean plus some error random term, right? And what is regression here? Regression model is almost the same idea here. Is the following. We have observation of I observation coming from unknown alpha, unknown beta, some fixed term x plus epsilon. Okay. And we also have the same assumption we want to make is this is 0 variance of this is sigma square covariance of epsilon I, epsilon j is 0, okay? And later we will also assume this is true. Epsilon I is also follow normal. Okay, so that is the two model that we are working on. And you do notice that this and this actually is different between ANOVA and regression, right? Is ANOVA, the group mean is a number that's fixed. We're not trying to explain anything. There's some group mean there. Yeah, that's it. Okay. But here, regression, actually, we are trying to look at the attribute or characteristic of the observation is not characterized as a group, but characterized by a variable called x, right? So this is the difference between ANOVA and regression, right? And in ANOVA, what we're trying to do is we're doing hypothesis testing. So H null is asking whether mu1 equal to mu2 equal to da 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 da, right? The same, right? Here, ANOVA will have the same, so regression with the same question. We will ask whether beta is being 0, right? If beta is 0, which means that everything is not x. The model actually, we don't need to worry about x, right? The same mean, right? The same idea, right? In addition, we can also ask another question is whether alpha equals 0 as well, or, right? So that's actually the two parts of the problem. Okay, so that is why the regression have more things, right, to answer. And if you remind ourselves that actually how we do the ANOVA is we do F-test, right? And how do we do F-test? Right, F-test is comparing the MSW over MSE, right? Is the comparison of variance, okay? And later you will see we can also do F-test here, okay? But in addition, we can also do t-test. Turn out to be is very convenient because turn out if this is normal, turn out beta already also a bell curve. Okay, so that's why we can do a t-test here, and we can also do a 2 t-test for the alpha, but we can still do F-test for beta. Okay, so that would be the thing that we'll talk about today. Okay, so basically this is the parts that we will be focusing on. Okay, because beta and alpha, beta and alpha is going to be we measure by A and B, right? The A and B are random variable, right? So A and B will also follow a normal distribution. Okay, so that would be the main idea that we are trying to do. I hope it becomes clear. I mean, as you can see later when we go over all the tests. And don't worry, there are almost few things to learn because most of the things we already covered already. So basically, what we talk about today is applying what we have learned. Okay, so there's nothing new concept. Basically, just applying those concepts we learned from what we have studied. So basically, just you just need to pay attention. Okay. So I guess next is the Gauss-Markov theorem, which sets the A and B from least square estimate turn out to be unbiased estimator. So the good thing is being that what if we are willing to accept, okay, this is our model that generate the data we observe, okay, you believe that Y and X underlying in the real world is related linearly. So that is the assumption we are making. Same as our ANOVA, we are making some assumption like how the data you observe. If you're willing to make this assumption, then A and B, we do the least square estimate. Indeed, it's an unbiased estimator of the real alpha and beta, and also the efficient as well. So that means that if you believe the data, say education and income, are within linearly, then you do the regression, you get the coefficient, that the coefficient you get is a good estimate of what actually it is. Okay, so I hope this will convince you that why we do regression is because we want to undercover what is alpha and beta. Now, if you only interested in point estimation, that we're almost done, okay? And the only thing left for this model is to calculate sigma square, to have an estimate sigma square, right? The reason why sigma square we want to know in this model is because this is a measurement of some random error, is how some kind of, say, how good is a regression? Okay, one measure how good regression is a regression, right? Because if your sigma square is large, right? Which means that y and x are not that tightly related, right? The smaller the sigma is, right, the more likely that the relationship between x and y are stronger. So you want to estimate sigma square, and the way to do is what we call the sample counterpart, that is also usually appear in statistic models, is what you try to see is the variance of epsilon, right? What we care is where's epsilon, which is sigma square, all right? What we want to estimate. Then how we try to estimate this guy is to form what we call sample counterpart, okay? And we basically we never know alpha and beta. So how do we estimate this guy is to replace it with our estimate, A and B, right? And once we place it, then we know this, we will call this as a residual, okay? And we want to calculate the variance of this residual, and this variance of the residual, the sample variance of the residual, will be our estimate for sigma square, okay? And turn out this is the sample variance, right? And I guess I talked to you about last time, right? You don't need to minus the mean, because if you try to do this, okay, this is with 0, okay? And so that's why you don't need to minus 0, okay? That's why we don't have square, okay? And and that, of course, that means this is E bar is 0, right? I mean, that's why we never see the E bar, right? We don't need the basically what I say, the sample mean of the residual is 0, right? And just another thing that I want to remind you a little bit is y minus 2 here is because we estimate alpha and beta by A and B, so we have 2 parameters less, so that's y minus 2, okay? So that is the reason why that's the case, okay? And we don't prove it here because the proof elaborate. That turn out, okay? You may ask why this is good. Turn out to be this unbiased estimator, okay? So that is the reason why we use this, okay? It's not because of this procedure will be usually we adopt, but really this is because this is actually getting what we want to get, okay? And if you only care about point estimate, right? This is how good your regression is, right? If you have a bigger S, okay, then you would put less confidence on your model, right? If you have less S, then you're happier, right? Your regression is likely to be better than the case of a higher S, okay? Is that okay? Okay. So now I guess I want to talk about hypothesis testing and estimation, okay? And we can't go further if you don't make any assumption on the epsilon, right? So we need to have, like before, we need to make sure that epsilon follow a bell curve, okay? If we follow the normal bell, okay, bell curve, then we can do a lot of stuff, okay? So that would be the goal of today, okay? We will, from now on, okay, we will make the assumption of the bell curve, okay? Before, up to now, we don't need any bell curve, okay? Point estimate would be sufficient for our purpose, okay? But from now on, we will do a bell curve, okay? I think I go over this already, right? Last class, right? Am I right? I go over that already, right? So I'm not going to, I'll go over that, right? So I'm not going to talk about this again, okay? So what we're going to do is we have our point estimate of intercept is A, right? So there are 2 actions we want to work on A, the point estimate. So the first is to see if use this to test is alpha is 0 or not, right? Because A is try to an estimate of alpha. What we want is we want to have the whether alpha is 0 or not, right? And how do we do that? Okay. And so first, without invoking this bell curve, so I want to tell you that we don't want to do the proof, but I want to argue that the intercept we get, okay, has a variance following this formula, okay? And you probably ask why this is true. The proof is in the slides, but I try to convince you this is correct, okay? So I think the first, there's a several item here. So the first one is sigma square, okay? I think you agree if the data has more variability, the A you get will be much more variance. Okay, let me illustrate by drawing a graph, then you would, I hope you will be convinced by that. So I will draw two different scenarios. Scenario one is the case where we have low variance, the other case high variance, okay? So remember, if the data is generated according to this manner, right, we have yi is alpha plus beta xi plus epsilon, right? And do remember this is population, right? So potentially, the data you get will be roughly something like this, right? I mean, you don't know which one you will get, okay? But it will be something like this, will be according to this line, right? And in other scenario, okay, you may be getting another line, okay? And let's consider the case this is have larger variance, okay? So the data you might get is something like this, right? Okay. And this is data generated in the population. But do note that you only do sampling out of these points, right? You are never able to get all the points there. So it depends really on the points you have drawn, okay? So it is possible, right? You can see from this diagram, you may end up this line if you run the regression because you get all the points nearby this line, right? You may also able to get this line, right? And you may also can get, if you are unlucky, you also may be able to get this point, right? And or this point, right? So you can see the A can vary like this, right? A is looks like, or the varies like this, right? So A can fluctuate, the intercept can fluctuate in this way, right? And as a comparison, if you look at this one, okay, if you are lucky, you may end up here, okay? You may also end up here. You may also end up here. You may also end up here, okay? So you can see the variation is much larger, right? So maybe I just write down the case, right? This is small sigma, and you have large sigma square. Is that clear? Y is proportional to sigma, right? If you have much larger sigma, then you will see these two different, okay? Of course, the real proof would really, you have to work it out, but I just try to explain why they make sense, right? This is how the line, they make sense. The second one, I guess I can also do the same procedure to show you that if you have more n and less n, okay, that would be different, okay? So what I'm going to do is trying to show you the same graph, a similar graph, okay? And the graph will have same sigma, everything the same, okay? The only difference about this is how many points you're going to get, okay? From your data set, from your sampling, okay? So suppose your data is again something like this, okay? I'm not going to make a difference, maybe here, 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 okay? Something like this. And here I also have something like this, the same. So I'm trying to be same, but hopefully I don't make too much deviation, okay? I consider case I have large n and this is small n, okay? So suppose the case I have large n means that I collect many data points when we do regression. In that case, maybe I pick up 6 points here, right? And turn out to be, it's more likely that it will be more center, right? Because I pick out more 6 points. Then it's more likely that I will get something like this, something like this, something like that, okay? Something like that, right? Okay, it's more closer because I take more points. But I have small n, then likely that I will get, say, I get this point and this point, I get 2 points, right? And the way I do regression, will likely that I will get somewhat like this, right? If I'm lucky, I get this point, right? I will get something like that as well, right? And because I only get several points only, right? So that means that I would likely to have much larger variation compared to case I will take many points, okay? So that means that I have more n than the intercept has different style, right? Is that clear? Why is the case? Okay. Because the more n you got, the line will be more center on the center, right? The less pen you got, the less sample you got, then you're more likely you have some extreme value, right? If unlikely one is getting lower, one is getting bigger, then you have a much bigger flip. Is that clear? Okay. Of course, I try to convince you this is the right formula, okay? And I'm continuing to convince you that why you have xi square, okay? The third part, right? Here is when xi is more, the variance A is larger, okay? The idea is also rather simple, okay? Let me do it here again. I hope by now you should be able to think why this is true, okay? So let's consider the following 2 cases. I have a case where sum of xi square is small, okay? That means that this is 0 here, right? This 6 is here, okay? That means that the data may be near here, okay? I just draw here, okay? And compare to another case where this is large, okay? And this large is something, I would have something like here, right? So that would be our goal here. And you probably can tell me what kind of regression you will get, right? And very likely in this case, let me use it, right? You will likely to get what kind of line you can get, right? You will likely to get at most between this range, right? You run this regression, this is the range you are going to get, right? Maybe you get here, maybe you get here, depends on what you get, but likely within this range, okay? But if you try to look at the blue one, what you get? You may get this one, you may get this one, okay? But you may also get this one, you may also get this one, depends, right? And you can see this is much larger than this guy, okay? So the further away, right, the data, okay, the more variance in terms of intercept. Is that clear? Is that clear why this is true? Okay. Is that clear? The variance of intercept is much larger in the first case of the second one. Is that okay? If that's okay, I want to explain the very last idea here. Why the denominator is the variance, right? It's more like the variance idea, but it's like the distance from the mean, okay? And let's see, okay, how you would explain that part. Okay. And this is how we do, okay? Again, I draw two different cases, okay? But first we need to come up with the x bar, right? Because this is the distance from x bar. So here I have x bar here, okay? And I have x bar here, okay? Look at your data, okay? Your data, because x bar, so your x must be some the x bar on the left hand or on the right, right? Because x bar is in the center, okay? Suppose your data is in this way, okay? Maybe easier to see, okay? And some data is there, okay? And your regression line will likely to be something like this one, right? And this one, right? Now consider the alternative scenario where your data is further away from x bar. So just a parallel shift outside, the same thing. Try to see if you can see the reasoning. Okay. Now, what kind of slope you would get? Okay. You would likely to get this one, right? Can also this guy. Can also you want to fit this, maybe like fit in this way, right? And right, sometimes can even this way, right? And this one really depends, but you obviously see that this and compared to this guy, okay, you can tell us which one's larger, right? This one you have this minus this is small, and this is this minus this is big, right? Because this is the square distance from the mean. Is that clear why these four factors are affecting the intercept? Okay, of course. If you want to know exactly, the proof is already in the slide. Okay, but in the technical graded area, which I'm not going to go over, if you're interested, but I hope I convince you that why you try to fit the line, this is the variance, right? Remember why the variance is because you only get randomly pick up some points from the data, right? So this not the whole, you don't get the whole, all the point you want to get, right? Because you're sampling from what is supposed to be in population. Okay, if that's okay, then I hope I can convince you this is right, right? And now everything becomes very straightforward. Okay, because this is follow a normal. Okay, and A. Okay, remember how we find A? A is y bar minus bx bar, right? But what is y bar? Y bar coming from each yi, and each yi is just A alpha plus beta bxi plus epsilon. Okay, so which means that A is a linear in y bar, which means that A is also linear in yi, right? Because y bar is just y1 up to yn divided by n, right? It's a linear function of A is linear in y bar, A is linear in yi, and yi is linear in epsilon. Okay, so that's why A is also a bell, right? Because it's sum 1 over n times each observation. right? So it's linear, everything is linear, right? Because Bell multiplied by 1 over n, you add all this observation, is also a Bell, okay? And turn out to be, right? So it just, this is a Bell thing, right? It's a Bell thing, okay? And now that is very simple, right? Because we know this is a Bell, right? Then we can just test it, right? Because alpha, what you get is, sorry, this is a big A, okay? The A is a random variable, and it's a bell curve at alpha. We know it's normal with the values like this, okay? Although we don't know sigma square, we can use S. Sorry, we can use S, right? So then that become a t-test, right? Because we want to see if alpha is 0 or not. Then we can just use t-test, right? Because we are testing whether a normal distribution, right? We draw a data from there, is whether normal or not. If you don't know, the variance you replace by a sample counterpart, that is the t. Okay, so that's why we have the following. I skipped the proof. Okay, you don't care about. So because whether it's 0 or not, you just subtract from 0, but indeed you just over because you don't need to subtract from 0, right? So this is, if you learn it's less than 0, but you just forget about the 0. Okay, you just over the standard error, standard deviation, right? This is t, right? And the only difference from what you learn, it's just n-2 rather than n-1, right? So this is the only trick that compared to the before, right? The only reason why you need to subtract 2 because you estimate 2 parameter A and B, right, for this one. So that's why you lost some degree of freedom here. Okay, but I don't think you need to remember now because you just need to know it's n-2, right? Why this is 2, then I have already hinted, but it's not proved anyway. Okay, so and as we have said, A is a point estimate, right? You can easily see that we can do confidence interval estimate, right? Especially when you have proven the t-test is you're going to reject the null, right? Then you can all do further to estimate what's the range, right? And because you don't know, then you use a t, right? So everything is straightforward as we have done, right? Because this is just normal, right? Just the same the t. So there's nothing new here. You found the critical value. Just to remind you that it's n-2 rather than n-1, right? So there's only difference, right? And that's it, okay? So let me go to the example of this, okay, quickly. And I'll show the Excel, how to calculate very fast, and then we'll have a break, okay? So today we're a little bit longer before the break because this part is slightly more involved, okay? And here, I hope you still know how to calculate yi, okay? Because we have A is 3.9 and B is 0.7, right? So how do you get this 4.6? It's just 3.9 plus 0.7 times 1. So that is how you get 4.6, right? And how you get this EI, it's just 4 minus 4.6, okay? So I hope you remember how you create this table, right? And the next is how you get this S, right? This S is simply, right? You just square each item there, right? So basically coming from 0.6 square plus 1.7 square, so on and so forth, over 5 minus 2. We have 5 data minus 2, and you take a square root. That gives you the S, okay? And now with the S, then we can use the formula we have just learned. What is the standard deviation or the variance of the intercept, right? You remember the formula is like this, right? The variance of A will be just sigma square over n, right? Sum of xi square over xy minus this guy, okay? So for this guy is replaced by s, right? So it's here. And here you just calculate sum of xi square is 55, it's 1 square plus 2 square plus 3 square, right? This is just 1 square plus 2 square plus 3 square, right? Plus 5 square, right? Is 55, right? And this is just when you do the thing, right? Just minus 3, right? This is just 1 minus 3 square plus 2 minus 3 square, right? And so on and so forth, right? Until you get to the 5, right? And this is 10, right? So that's why when you put all the number here, you get S of A is 2.191. Okay, so that is the thing we got. Okay. And lastly, we want to do a t-test. Okay. So it's very simple, right? Because we got the 3.9 is here, right? The 3.9 here. We just put the denominator 2.911. That gives you the t-test is 1.799. Okay. And that's almost done, right? Because remember what we're actually doing is this, right? This is A. This is alpha is here. We assume to be 0, right? And we are basically converting this to the t, right? This is 0, right? And we'll figure out this is the data we have is A is 3.9, right? We want to know if this area times 2 is it smaller than 5%, right? Or do the critical value method, right? And that translates to this diagram is 1.779. So again, we want to check this area. If this area times 2 is less than 5%, then reject the null, right? And here I use the critical value method, right? I check the critical value, right? Because it's a two-tailed test, okay? The critical value is 3.182, right? Just to remind you at this point, I think now by now you should know how to do it, but you have to do it T inward, right? 0.975, 3, right? So that is how you get this number, right? And this number is actually turned out to be way here, right? 2.5%. So in this scenario, you can't really reject. All right? I think I don't. And how to find the 95% confidence, right? Just do the same. Just put this number here, right? And this is here, right? I don't think at this moment you need me to show you this one. Okay. And although these calculations are straightforward, usually you don't need to worry about this because Excel will directly hand out everything to you. Okay. Now I show you how to do this, then we have a break. Is there any question before we proceed? Because when we do Excel, we will have all the results just by one click. Okay. Is there any question before we proceed? Okay. If there's no question from you guys, then I will just go to the Excel very quickly because you make I think we'll use 5 minutes at most to do it. Okay. Now let me copy the data here. Y is here, X is here, is 4. 1, 2, 3, 4, 5. Okay, this is the data. Now, what I want to do first is to remind you the two functions that we learned last time. We do the intercept, and the slope function. Okay. And let me save the file because I'm not sure how stable this data is. Okay. And how do we do that? It's just intercept of y and x. Okay. So this is how you get the intercept, right? We did that last time. Okay. And we can do the same for the slope. Put bunch of y here, bunch of x here. Okay. So this is how you get the slope intercept. Okay. So another one that I want to show you is you can get the S, right? It's called STEYX. Okay. This will give us the S. Okay. So it's the estimation of sigma. Okay. So you just do the same. Okay. So this is S. If you remember 2.89, it will be this one. It will be just this number. This S is given here. Okay. So now what I want to show you is we will give you use the Addin to do what we want to get. Okay. So what we do is go data. Okay. If you suppose you should have analytics here. Okay. But in this it's not, so you just go there to Addin. So I show you how to do Windows, but I know many of you have Excel. Sorry, using the Mac, but that will be somewhat similar. So I enabled analyst to pack. I think we'll do this many times enough, so I'm not going to repeat it. So for this, I'm going to create another copy. Okay. This I will do Addin. Okay. And I don't really need the this column. I just erase it. Okay. So what I'm going to do is make it smaller. Okay. I'm going to use the regression Addin to handle regression. Okay. That will make things easier. Okay. I start data analysis. And here are the regression. Go to the down. There's a regression here. The regression. Okay. Okay. Then it's very simple. I just need to tell them what is my y and what's my x. And that's it. Okay. So the first one is where to put the y. You tell them from A1 to A6. Okay. For some reason, you cannot just give them the column. For input x, it just go from A1 up to A6, B1 up to B6, sorry, B1 to B6. For data, we have label, so just click label. Okay. And you don't really need to worry about this because 5% is default already. So unless you want a 90%, so you just keep them there. And just tell them the output range. Okay. And usually we want to output in the same sheet as we want, so we can look at it. Okay. Now you're done. Okay. So basically telling X, telling Y, telling your labels and where the output. And click OK, then you're done. Okay. So basically this is they give you all the table that actually we are learning from this class. Okay. And indeed is actually the thing we learn today. Okay. So this is S, right? Is something that I think we just have mentioned STEXY, right? And this N, we know how to do it. Okay. And later we will learn this guy R-square, okay, which is later we will see is how good is the regression. Okay. And the multiple R and just R, we will not need it. Okay. So let me use the gray color to highlight that we are not using this. And you will probably ask, what are those? These are the thing that when you learn more than linear regression, simple linear regression, when you have more than one variable, then this thing will be meaningful. But for our purpose, we just focus on R-square and that's it. Okay. And you should able to later see after the break, we'll go over the ANOVA And what you learned just now is we learned this one. This is the what we found, right? The coefficient, right? This is the guy we know. Okay. And this is guy where we calculate 2.191. If you don't remember, this guy is right. This is actually the standard error S of A, right? S of A. Okay. And the T will be just you divide this column E by column F is this guy, right? That's what we learned, right? It's column E over column F. And P value, I think is simple, right? Just calculate the value of that, right? Just to remember the degree of freedom is just have the n minus 2 is 3, right? Just in case you don't, will be just 2 times 1 minus, right? T dist of this value, right? And degree of freedom is actually 5 minus 2, which is 3, and true. Okay. So you can see how I get this formula here. Okay. And these two are the interval, right? I think it will be the same as you would see in our slides here. All right. So I think the goal is of this topic is enable you to understand every entry in this table except the grade one. Okay. Because the grade one is not relevant for our purpose anyway. You will only use it when you have more than the data is more complex. So for the moment, we don't need to worry about those. Okay. So any question? If no, let's a break of 10 minutes and I go around to check if you have any question. And yeah, so then we'll basically finish this for the rest of the class. Basically, you understand every single thing in this diagram, and then we're done. Down there. So I guess we resume. So don't worry, the rest will be just trying to make sense of this table, okay? So that's nothing new, but try to make sense of everything there in this output, okay? So probably you would expect after the intercept, what we do is try to do the same for the slope, okay? What we do is try to see if the slope is 0 or not. It is more important than intercept because the slope tells us whether your y can be explained by x, right? Because typically just like whether if you look at y is your income, x is your number of schools, right? You want to see whether schooling is affecting your income, right? So that is the idea. And you would expect to see the B, okay, I'm not going to prove it, is related to sigma and inversely related to xi bar. And the idea is actually similar to what we have seen. Go back to here, okay? The same idea here, look at the B, look at slope. Which one have more variation? Obviously, the right-hand side would have, right? Have a less variation, right? Sorry. So we are looking at the same idea, right? So this one gets smaller, the variation gets smaller, right? So exactly the same as we would expect for the A, right? This one we have bigger variation compared to the right-hand side, more comparison to the left-hand side, right? Maybe if you want, I can just the B is like this, right? And this is the A like this, right? So you can see that is the reason why it's inversely proportional to this one. Okay? And you can also go back to the idea of sigma, right? You also can see if you have different this, right? The variation of the slope is like this, okay? Not too much. But this one, the slope is like much more, right? So that gives us the same idea here, right? So that's why the variance slope is proportional to sigma and inversely proportional to the distance, the variance of x, okay? So that I hope kind of convince you this is right, of course. The ultimate proof would rely on actually the mathematical proof, okay? We cannot replace intuition, okay, by math, but we can use intuition to understand the math, okay? And the same, everything the same. You have B here, right? You have the beta. This is the new formula here, right? You can do the same tricks, okay? So I don't think I need to really go into detail because the same thing here, right? So everything the same, right? And just go to example. I think it's suffix because there's nothing new from what we have done. Okay. So every data is the same, right? So the only thing here is this guy, right? Because now the variance of B, right, it's just coming from sigma square over this guy, right? Much simpler, right? The only thing is you just replace using the S to estimate, right? So this S, right? Go to here, okay? So to remind you why I use the t-test here, because we are looking at the mean, right? We're getting what we are actually working on is the following, right? Remember, the idea is B, okay? We have a bell curve, okay? And this bell curve, because under Gauss-Markov theorem, this is beta, is here, right? It has a mean beta, right? The bell curve comes from the fact that you assume, we make assumption on the epsilon of the bell, right? Why the bell here? Coming from the fact that we assume the epsilons are bell, right? Remember, this is the assumption here. This is where sigma square, okay? And if you have this, the variance is actually sigma square over the sum of, right? So that is the sigma square, okay? That's the idea. And the idea is what you get, right? B in your data turn out to be 0.7, right? 0.7. Okay. Under the null, this is 0, right? 0.7 is somewhere here. Okay, somewhere here, 0.7. Okay. What you want to do is to check, right? Is this area times 2 is very small, right? Because the thing is, we want to see beta is 0, right? The data we get is 0.7. We want to see if 0.7 is different from 0 big enough, right? How can we do it, right? The way to do is look at the area on the right, right? Times 2 is just small because we're doing two-side tests, right? And the thing is you transform it to t, right? Because you don't know the sigma, right? You don't know this guy. So we just transform it to t, right? This is 0. And transform to t, this guy, 0.7 goes to become 1.059. This is what we have, right? You just over our estimated or standard error, right? So turn out we want to check out this area. Times 2, is it bigger than 5% or less than 5%, right? One way to do it is not look at the thing, but look at the critical value, right? Look at this value, right? Turn out if you want this like 0.025, right? And this value turn out to be 3.182, right? So that means that your beta is not, your B figure is not too far away from beta, right? So that means that you can't reject, right? So here you have B here, right? And the critical value is here, right? If you 0.06 is here, right? So if you want to do a 95% confidence level, that is how you get it, okay? So all the procedure is the same, right? Same as you do intercept, okay? So I don't want to spend too much time on this one. And actually you will, you know how we do the first one. This one will be exactly straightforward. And I want to draw your attention to how you do this, right? This is how you do 0.7. This is how you do 0.6, right? So that's how you do all this three, right? I hope you know how each entry comes about, right? You should be able to see how you get this one, or entries no, okay? Of course, the assignment just asks you, basically, just you run this in your Excel, you just tell me the number, right? So that would be the assignment that I'm asking you. But I hope for your, you know how to get these numbers, okay? From how you construct, how they're related, right? And anyway, we will look at the review paper next week, and we will see more interesting question coming from this, okay? Right? Is that okay at this moment? Okay, so I hope you know how they're related and how to read this table. It's very important, right? And I guess now what I want is to try to explain this ANOVA table to you. Okay, and that's almost all of today. Is just go to this ANOVA, and that's almost it. Okay, so what I want ANOVA is comparing variance. Okay, so as later you will see, that's why we do F test. Okay, the idea is very simple. Okay, ANOVA is analyzing variance. That means that I will divide things into 3 different parts. Okay, actually 2 parts. The first part we're going to set is what we call called SST, same as what we have learned in the ANOVA. Is we forget about the groupings. We forget X. Okay. What is thing we want to explain is how each observation different from is Y bar. Why is it the thing we want to explain? Okay, this is the part we want to explain. Why? Okay. It is the reason is if we have no idea of X, okay, or we don't have the model itself, there's no X, okay. If you pick up a particular guy, okay, from the population, what would be an expectation to that guy? Is the sample mean of population mean of Y, right? Y bar will be your guess. Okay, for example, you are going to look at the income education. Okay, suppose you don't know the education. What is your prediction of this guy's income? It's the average income of the population, right? You don't have no information about his education. What will be the guess of his income? It's just the overall income of the group, okay, the population. So the difference will be the thing we want to explain. Okay, is the thing that we want to explain. Okay, because this is our naive, what we say, the naive guess, right? It's naive guess. Okay, and the one that actually explained by our model, okay, is Y hat minus Y bar. Okay, it's the thing that explained it in the model. Okay, I think it's good at this point to draw a diagram. Okay, although it will appear also in your slide as well, but it's good to have a diagram at the moment here. So I have X and Y here. Okay, now I have a bunch of data points. Okay, this is my regression. Maybe I use other color. Okay, this is my regression. Okay, my regression is the Y hat. Okay, and remember our raw estimate is Y bar. Right? So the things that actually we in the model we want to explain, right? This is the naive model. We want to explain is all this, right? Okay, and all this. Suppose I use this guy. So this is SST, right? SST. Okay. SST is being the sum of all the observation you got minus the bar, right? Now, here we have is this distance is SSR. SSR is being summation of yi minus y hat minus y bar. Okay, is the hat is the line minus the bar. So basically, it's just like the part that not given by the y bar is coming from the x, right? The reason is why, if you do recall that the regression line will passing through the area where you have X bar here, right? This is the line, vertical line X bar, right? So why you would say Y is here? It's because X goes up by from here to here, right? So what is the green thing here, right? To explain the path is coming from Y is what you predict Y this line, because X is what you have in this point. X is actually okay, green is easier to see if you remove that point, right? Because X goes up in this much. That's why, look at the line, Y go by that much, right? So that's why you mean that why you say Y is more than Y bar is because X is more than X bar, right? And this is how explained. So this is SSR, okay? And you can easily see that what is not explained in the model is called SSE, okay? And SSE is being that the summation, okay, of the yi minus yi hat square. Okay, so this is the yi, the height, right? So yi, and I put it here. This is yi hat, right? And this is a y bar. Okay? So that's how you get all this, okay? And it can be shown, although we don't prove here, but you will see from this diagram, it's pretty straightforward. This is equal to this. So the total variation, okay, the total thing we want to explain, basically just like the thing we want to explain, okay, is can be divided in two parts. One part that is explained by the regression. The other part, that is, this part is not explained. Okay, so that is the first thing we will see is the thing we want to explain actually divided in two parts. One part is explained, one part is not. I think that is pretty simple. Okay, and that would mean we will have one thing we learn is called R-square. Okay, R-square is defined as, very simply, the part that you have explained, the part that you want to explain. So it's SSR over SST, which this because R-square on the slide sometimes refer to coefficient of determination, which is always between 0 and 1. Okay, is that clear? So first thing is R-square is the thing that we want to look at. So go back to the Excel, it actually is there. Okay, this R-square. Okay, in this particular example, the regression actually explains 27 of the data. Okay, or you can calculate the SSR over SST. So it's just 44.9 over 18. So give you this guy. So let me actually work it out. Okay, this is just 4.9 over 18. Okay, so that's how you get this formula there. Okay, so I hope that's clear what we get. Okay, this is a SSR, SSE. Okay, is that okay? Okay, so let me go back to the whiteboard. Is that clear what we have? Is that okay? Is there any question? Any question? Is that okay? Now, here, I want to say one more thing is we can have another test of beta. Okay, we can use the idea of ANOVA to test the idea whether beta is 0 and beta is not equal to 0. How we can test it? Okay. SSE, okay, can be a measure of variance, right? Because look at how it's like the within group variation, right? Look at how each observation different from the line, right? So this is, you can come up with a measure of variance from SSE, okay? That actually we will call MSE, okay? This is a measure of variance based on the departure from the regression line, right? And do look at under if beta is 0, right? If beta is 0, the line is supposed to be a flat one, right? Then SSR, what you get is MSR, okay? You calculate the variance of based on this, right? How the line is different from the Y bar. This also gives you a measure of sigma square, right? Both will give you sigma square. If the line, the beta is actually 0, MSR shouldn't bigger than MSE, right? Under this case, MSR should be similar to MSE, okay? If this is the case, MSR will be greater than MSE, okay? So basically, you are comparing two variants, right? Then that gives us the F-test. We are comparing the variance measured by the idea SSE and SSR, right? The variance measured by this one should be similar to this one if actually it's a flat curve, right? But if not flat one, the SSR will be much greater than a MSE. That's why I justify our F-test. Is that clear? Because it's based on the idea of variance comparison, right? Because is that clear why this is true? Is that okay? Let me repeat because it's very important, right? Actually, same as ANOVA, we do the one-way ANOVA, right? Looking at within group and outside the group, right? Compare. Here is you compare the variance of each point to the line, okay? This gives us a measure of variance. And look at how each line from the center, right? And if the line is not flat, right, then it must, the SSR would contain how it sloped and what the error, okay? So that's why if the beta is not 0, this is much larger than the other one. Is that okay? If that's the case, then if you're okay, then we go to okay. So I think this is the graph we have just drawn. Okay. We also said this is coefficient of determination. Okay. And how we calculate this, I think that should not be an issue, right? Basically, you just you have the x bar, x hat, right? X hat, remember, is a plus bxi, right? And you just do the subtraction. I think it's straightforward, okay? And SST, just by definition, right? It's just SST, just summing all this column, give you this, okay? You square this, right? And the SSR coming from the regression from the bar, this is the SSR, right? And the SST coming from this guy, right? Okay. And the ratio of the SSR SST is the R-square, okay? So probably one thing I want to mention is how R-square is related to the correlation coefficient you learned in topic 1, right? We learned the correlation coefficient, COR, right? Is what? Is covariance xy over square root of variance x, variance y, right? This one. turn out in our simple linear regression, if you take square of this guy, it's exactly R-square. Okay, so that's why sometimes this R in some book they refer to small r. Okay, but anyway, that is the idea of R-square. Okay, just to prove this in the Excel, let me go to Excel here. Okay, we have R-square, this one, right? So let me show you. You can do R-square. Okay, first thing I want to show you the R-square, the Excel. Okay, as well. Let's see. Okay, R-square is called RSQ. Okay, you can do the same. RSQ, bunch of Y and bunch of X. This is the R-square. Okay, so explain 20%. But this is also the same as you do the correlation square. If you remember, the CORREL is what we did in the topic 1. Okay, the covariance over the square root of the product of the variance. Okay, you get the Y, you get the X. Okay, so if you CORREL square it, okay, you just square this guy, give you the same result. Okay, so that shows you the R-square is closely related to the correlation coefficient, right? So I hope that's not surprising. Actually, it's pretty intuitive, but the proof, of course, we don't do the proof. Okay, and as we said, we can do mean square error. Okay, and the SSR divided by 1 with the MSR. Why 1? Because only have one group, right? Whether you are group in or group out, right? So that is only 1. Okay, and the MSC is just n minus 2. Okay, remember this is S squared, right? So this here we have 2 ways to measure sigma square. Okay, so they are comparing sigma square. Okay, under the null. Okay, so under the null hypothesis they are 0. Okay, okay, then this is just F test with 1 and minus 2. Okay, and this is going with the right tail test. Okay, because you would expect the SSR is bigger than MSE, right? So this is the same as what we do ANOVA, right? There's nothing new compared to one-way ANOVA, right? Just like within group and compared to between group, right? The between group is much larger than the within group, and grouping only have one group, right? Whether you are on the line or not on the line, right? The grouping is a line. Okay, and I think this is pretty straightforward. I guess it's best to go back to the Excel and show you the result, right? And here you can see, let me enlarge it. Okay, we have here we have this entry is SSR, right? And this entry is SSE, right? And this entry is SST, right? And why you have 3 here? This is just n minus 2, right? And you always, for regression, you always have 1 for our case, right? Because we only have one variable, so we always have one grouping. And if you this divide this, you get 4.9, and this divide this, you get 4.33, right? 13.1 divided by 3, right? And next you take the ratio, right? Remember F is what? F is just MSR over MSE, right? Just to remind you, this is MSR and this is just MSE, right? And this is one tail test, right? So basically you check this based on that one. Okay. And in case yes. Okay. Is that clear? So there's no difference from the ANOVA when you do one-way ANOVA, right? The difference is whether you know the degree of freedom, and that's it. Okay, it's a bit slightly different, but everything stays the same. Is there any question? Is there any question? Any question? If no, we just left the very, very last thing we want to mention. Okay? Is there any question? I think the last 5 minutes we'll talk about this. We are done. Okay. So the very last thing is here. Okay. Oh, before I do that, I forget about one thing. Is how this F and this value are related. Okay. So turn out to be this value F, and that's T is divided by square. So if you take square of this number, okay, would be same as this one. Okay, so just make sure that I would like to mention is this T value, your squared is same as F1. Okay, and that tells you the F test and T test are the same thing. Okay, in our context. You can do either of them, will give the same result because T is telling us whether the beta is 0. This is all the same. Okay, so that's why you shouldn't be surprised to see they are related in some relationship, right? Because is that okay? Any further question? Okay, if no, we'll go to very last thing we want to mention. Okay. So the very last thing is actually it's rather simple. Okay, bless you. So the thing what we want to do is to actually utilize this model, right? So far we just talked about, okay, we proved there's a slope there, right? And we didn't actually use it. Okay, so suppose the data, we just run the regression. Now we have a line, and this replaces the data we have, right? We have a bunch of data, but now we no longer care about data, okay? Because now with the line, this line establishes how we know the relationship between A and X and Y, right? This line summarizes the information or condense the information from data. So this is what we have, right? So naturally, we want to use this model, right? So what we want is, okay, suppose I have X0, okay? Which in this case, I have education. I want to guess what's the income. So what we're going to do is to say this one, okay? This is our guess, right? Our guess will be A plus BX0. So this is our guess of what Y should be, right? If you give me a particular X, okay? This is our point estimate of what Y should be, right? And what we want to know further would be what is the interval estimate, right? So we have this model. This gives us the point estimate. We want to construct a interval estimate. How do we do that? Okay, it's very simple. We need to know the variance of this, okay? And the variance of this will be related to this expression, okay? I think everything is very obvious except for one, except for this guy, right? Other things should be relatively intuitive, okay? The only thing that is surprised us is probably is this one. The distance of your data from the x mean of x. Okay. It does mean that if you try to predict y based on x, if your x is far away from the data mean, your accuracy will be limited. Okay. So basically, if your data is all here, okay, if your x is somewhere further away, right, from your, say your data is like this, okay. If you are way further away, okay, you put the variance you're going to put will be very large. Compared to A, your variance is much smaller. Okay, this will be your confidence estimate, but if you have this, your confidence will be much larger. Okay, so that is what I lastly want to say. Okay, so basically this is the formula for the variance. You replace by S and take a square root. This is the standard error, and that's the last line, right? So this is the point estimate. This is the interval estimate, and that's it for today. I guess I don't have anything more to say besides that, and I'll upload the assignment later today. That would be where you should do it very fast, so it shouldn't take too long time. Okay, for this, the last one. And again, if you think you already get a good grade from the first 5 assignments, you don't need to bother the last one, because I'll take the best 5 out of 6 one. So you don't need to worry. Because I want the earlier deadline, because I want to release the solution. But I guess it's very straightforward. Even though I don't release the solution, you don't have any issue anyway. But anyway, I will see you next week. Next week we will discuss the past paper and Q&A. If you have any question, you can just email me in advance, or you can ask immediately. Okay? So I'll see you next week. Have a nice weekend.